Hello and welcome again to our journey into linear algebra, and in this little section we're going to look at systems of differential equations, which is going to give us a nice application of the earlier section we did on the exponentials of matrices. Now, the first step is to write our system in matrix form, which is best seen by looking at an example. So here's our system of differential equations. We're looking for two functions, y1 and y2, functions of, say, x, or t perhaps, so that if you differentiate the first function, then the answer you get is 8 times what you started with minus 10 times the second function. If you differentiate the second function, you get 5 times the first one minus 7 times the one you've just differentiated. And we have some initial conditions that y1 at 0 is minus 1 and y2 of 0 is minus 4. And we'd like firstly simply to get matrices into the story in the obvious way. So to do that, we're going to simply take this and convert it into matrix form. So there are the equations I just went through. And we're going to let vector y be these two functions, y1 and y2. And write that as a vector. And then so this expression here, y1 dashed, y2 dashed, I'm going to write as just y dashed. And then if we look at this here, we can write this obviously as 8y1 minus 10y2 by matrix multiplication, and 5y1 minus 7y2. So this is just a nice way of representing this system of simultaneous equations in vector form, and this of course is our vector y. In other words, we've got y dashed is equal to ay. So y, the derivative of this vector y, is just this matrix times the vector itself. And immediately this is starting to look a little bit like it's going to have something to do with eigenvectors and eigenvalues. And the initial conditions, y of 0 is minus 1 minus 4. So here we're just expressing this thing in matrix form. Now, of course, this obviously is going to generalize. So the general form for an n by n system of linear differential equations with constant coefficients is going to be in this form. Y dashed is ay, where a is a matrix, and y of 0 is going to be some vector c, some initial condition c. Now, you may say to yourself, well, yes, I did things like this back in earlier courses in eigenvectors and eigenvalues, and it's one of the applications of eigenvectors and eigenvalues, and indeed you would have been correctly told then, if you've got an n by n matrix A which has a full quota of eigenvectors, v1 up to vn, so you've got n linearly independent eigenvectors for this matrix with corresponding eigenvalues lambda 1 to lambda n. Let's put a comma in there. Then the general solution to y dashed is ay was simply given by y was a linear combination of e to the lambda 1t times the first eigenvector plus e to the something times e to the lambda 2t times the second eigenvector plus and so on, where these alpha 1s up to alpha n's are constants which can be determined if we have sufficient initial conditions. So I was going to do one quick example of this sort of method that you would have perhaps learnt in earlier courses in applications of eigenvectors and eigenvalues, and you would have seen something like this. So here is the system that we're starting with. Here is the system here. There's the initial conditions. We've already seen before how to write this in matrix form, which we've done before. So we put vector y as y1, y2. The system then can be written in this matrix form. I'll call this matrix A, and there's the initial conditions. Now a little bit of analysis on this. A turns out to have eigenvalues minus 2 and 3, which are calculated, and the corresponding eigenspaces turn out to be 1, 1 and 2, 1. which I leave you to check. They're the eigenspaces for this. You can sort of almost do it instantly, because you can see for minus 2, you're going to add 2 to the main diagonal. That'll give you 10 minus 10, 5 minus 5, and so you'll need span of 1, 1. And if you subtract 3 off the main diagonal, you'll get 5 minus 10. So if I take 2 of those, 1 of those, that'll be my second eigen vector corresponding to lambda equals 3. Now, using what you've learnt before, you can just write down what the general solution is. It's going to look like a linear combination of e to the lambda, so this is the eigenvalue minus 2, and there's the corresponding eigenvector, and then alpha 2 times e to the 3t times the corresponding eigenvector. Now we can get we use the initial conditions to pin down what these constants are. So y of 0 is minus 1, minus 4. So if I simply put t to be 0 in, then all the exponentials disappear, become 1s. And so I just get this is equal to alpha 1, 1, 1 plus alpha 2 times 2, 1. And it doesn't take too much work to solve this, and you'll find that alpha 1 is minus 7, alpha 2 is 3. So plugging that back up into here, there's our solution to the system of differential equations. And from that we can read off the top component, read off the bottom component, and that'll give me the y1 and the y2. So these were the two functions of t that I was looking for that satisfy the simultaneous differential equations. Now, an alternative method for this is to do the following, and it's an alternative method, and it's actually much more general and more useful, in fact. It comes from the following result, that the solution to this equation star, remember, was, I'll put it up here, was y dashed is a y, with y0 is c. So there was our system of differential equations with initial conditions, and this theorem says the solutions to this system of equations with this initial condition turns out to be just e to the at times the vector c. Solution is just the matrix e to the at multiplied by the vector c. So I'll give a little proof of that one, just to show that it works. So here's just a short proof of this. So all we have to do is, there's our system, and there's the initial condition. And I claim that y equals that is the solution. I'm not really going to check uniqueness. I'm just going to show, in fact, that this does, in fact, satisfy this equation here and the initial conditions. So first thing I've got to do is I want to take this and I want to differentiate this with respect to t. Now, as you might guess, if you differentiate e to the at with respect to t, as you might hope, you just get a e to the at. Now, you've got to be a bit careful because these are now matrices here. So let me just assume that for the minute, and I'll come back and show you why that's true in a second. And then, of course, e to the at times c is just y. So that means this formula here satisfies the system of differential equations. And if I put t to be 0 in, then you're going to get e to the a times 0. That means you multiply every entry in a by 0. That'll give you the 0 matrix. And e to the 0 matrix is just the identity, which you can see if you just go back to the definition of the e to a matrix. You'll get the identity. Identity times c gives you c. So it satisfies the initial condition. Now, the only thing not clear is the fact that if you differentiate e to the at, you actually get a e to the at, as you might hope. So a quick little note on that here. You go back again, as always, back to the definition. So the derivative of e to the at with respect to t is the derivative. You expand this out in series, I plus at plus a squared times t squared on 2 factorial and so on. Now this is a power series, and you will know from analysis courses, I hope, that you're allowed to differentiate power series and as long as you stay in the realm of the region of convergence, nothing goes wrong. Well, the series for E converges everywhere, so there's no problem here. So I differentiate everything term by term. So these are just constants. I differentiate this, I'm just going to get nothing. You differentiate AT with respect to T, you're just going to get A. And then, because T now is just a real variable, you differentiate T squared on 2 factorial, you get 2T on 2 factorial, and so on. And then out of that you can factor an A out, it'll be a common factor, you'll get an identity. You'll have an A left. 2 on 2 factorial is just 1, so that gives you AT. 3 on 3 factorial is 1 on 2 factorial. And I've taken an A out. And of course you'll observe here that this is just e to the AT. So differentiating in this way is allowable. So we can resolve, we can now go back and resolve this problem that we had before, but before doing that, we to assist us in calculating e to the AT times c, because I don't want to work out e to the AT if I can get away with it, then we recall the results from the previous section that we had. We had this in the previous section when we were looking at exponentials of matrices. And remember, it said that e to the AT, if v is an eigenvector, then e to the AT times an eigenvector. This matrix times this eigenvector gives you e to the lambda t times that eigenvector. That beautiful result here. So I'm going to use this idea when I come to calculate this beast up here, e to the AT times c. You can, if you will, work out e to the AT, but I like to not ever look at this matrix. It's pretty awful in general. I want to see what it does, not what it is. So I'm going to resolve that that problem, the one we did before. This is exactly the same problem we had before. Same initial conditions. I'm going to resolve this using this idea of multiplying e to the AT times the c. So here it is here. There's the system again. And once again, we're going to let y be y1, y2, whack it into matrix form as we did before. There's the initial condition. Now, as we saw before, this matrix A has two eigenvalues. Lambda is -2 and 3. And we have the two eigenvectors are 1, 1 and 2, 1, as we calculated before. The solution then, according to our theorem, is this matrix e to the AT times the vector -1, -4. That was our initial condition. Now all I do now is I'm going to express this vector as a linear combination of these two eigenvectors. And with just a little bit of fiddling around, I discovered that this vector is -7 times this vector plus 3 times this vector. And you can check that works. That's 7 -7 plus 6 is -1, -7 plus 3 is -4. So that was I just expressed this as a linear combination of the two eigenvectors. Now, when I multiply this in then, I can take that -7 out, and I just get e to the AT times 1, 1. I can take the 3 out, I get e to the AT times 2, 1. Now 1, 1 was the eigenvector for lambda is -2, and 2, 1 was the eigenvector for lambda is 3. So when this matrix hits this vector, you just get e to the -2t times the vector. And when this horrible matrix hits this vector, you just get e to the 3t times 2, 1. And finally, splitting these up into their components, we get y1 is -7 e to the -2t plus 6 e to the 3t, and so on. And that's exactly what we got before when we did it the other way. Now, alternatively, you can always, if you like a little bit of pain, you can work out e to the AT explicitly and then multiply it by the initial condition. I prefer this method of expressing my C vector in terms of eigenvectors and then using our lovely formula that e to the at times an eigenvector gives you e to the lambda t times that same eigenvector. Well, this of course all works beautifully if you've got a full quota of eigenvectors. Either method works nicely. In the case where we do not have a full quota of eigenvectors, then we need to use some of the ideas from the previous chapter on generalized eigenvectors, and we'll have a look at that in the next video.